This is 4.2, number 67. We're trying to find regions of concave up, regions of concave down, and inflection points. So you need to know where to find inflection points. The only place a function can change from concave up to concave down or vice versa are points where the second derivative is 0 or the second derivative does not exist. It's very similar to increasing, decreasing. If you can find increasing, decreasing, and relative max and relative min, if you do the exact same thing but use the second derivative instead, now you find concave up, concave down inflection points. So it's very analogous what you do with the first derivative and the second derivative. As long as you know first derivative tells you increasing, decreasing, second derivative tells you concave up, concave down. First derivative, if it changed from positive to negative, you have relative max. Negative positive, you have relative min. But for the second derivative, if it changes signs, you have an inflection point. So the process is exactly the same. You make the box, you test points around it. So if you know one, you should know the other, but make sure you understand the concept, because if you start to memorize, you'll confuse the two and you won't know what you're doing. So we need to find the second derivative to find concavity. And you should see this is a product. You're multiplying two things. And in fact, the first one I can rewrite as a 1/2 power, so I can use my power rule on it. So let's do a product rule to find the derivative. I leave the first alone, take the derivative of the second. I take the derivative of the first, I leave the second alone. This looks very familiar to me. Now the first part, I can simplify this. If I have exponents the same base being divided, I subtract the exponents. So this is x to the 1/2 minus 1 plus 1/2 x to the negative 1/2 ln of x. So this simplifies to x to the negative 1/2 x to the negative 1/2 over 2 ln of x. I have a common factor. I can factor out the x to the negative 1/2 and the 2. And again, some say, you don't have a 2 on the first one. Oh, yes, I do. You just don't see it. So I'm going to take out x to the negative 1/2 and a 2. What's left? Well, if I take out that 2 and that x negative 1/2, I'm left with a 2. If I take those two out, I'm left with ln x. There is my first derivative. I'm going to rewrite that. All over 2 radical x. Because the negative moves out to the bottom. That's why it's down there. But let me leave it as a 1/2 power instead of a radical. There is the first derivative. Now we need the second derivative. Now we need to do the quotient rule. So it's low, d high, derivative that's 0. The derivative that's 1 over x. Low d high minus high d low. Well, the derivative bottom, power rule, I move that in front. I end up with a 1x, subtract 1 from the power, and it's negative 1/2 over low squared. Ooh, I see a lot of work in my future here, a lot of work. So I'm going to do the same process here. I'm dividing, I subtract the exponents. So it's 2x to the 1/2 minus 1 minus, and I'm going to leave all this as is because I see something about to happen that I like. And that'll be 4x. Square that, you get 4. Square that, you just get x. Now, a lot of algebra here. 2x to the negative 1/2 minus 2 plus ln of x, x to the negative 1/2 over 4x. Here's a beauty. Look, common factor. I can factor that out. So I'm going to take out the x to the negative 1/2. If I take that out, I'm left with the 2. And if I take that out, I'm left with that. So it's going to be 2 minus ln of x all over 4x. This is a lot of algebra. We'll keep going. That moves to the bottom. So x to the 1/2 on the bottom. And on top, we distribute that minus. And so we end up with 2 minus 2 plus ln of x. And those will cancel. Wow, that is a lot of work. I hope I didn't make a mistake anywhere. That would be sad. Oh, you know what? Let me go ahead and combine these while we're at it. So on the bottom, we're going to have x to the 3/2. Why? There's a 1 there and a 1/2 here. You add exponents, you get 3/2. Wow, all that work to get the second derivative. I hope that's right, or else this is going to be a lot of work for nothing. Okay, I want to find where the second derivative is 0 or the second derivative does not exist. Where does it equal 0? When the numerator equals 0. I both sides to get rid of the ln. Those cancel. X is e to the 0, but anything to the 0 is 1. There's one point where the concavity might change. I set the denominator equals 0 because that means that the second derivative does not exist, and that clearly x is 0. So I have two possible places of inflection. So now, just like on the first derivative when we find critical points, we found where the second derivative is 0 or undefined, 0, 1. And before we proceed further, let me see what the domain is of this. Is there restrictions? Okay, there are. You all, by now, should know that the ln function looks like that. So this function has limited domain. It's only where x is positive. And this has limited domain. It's only where x is positive or 0. But you need to do the domain of this would be anything greater than 0, not including 0. So what do you say about this 0 here? Since it's not part of the domain of the function, you actually ignore that. It's not a critical point. So we actually are going to get rid of that and only have one critical. No, it's not a critical point. A critical point is when the first derivative is 0 undefined. It's where the second derivative is 0 undefined. It's a potential inflection point. So I'm going to find x in f double prime. If you are confused why you put f double prime there, you don't know what you're doing and you've memorized. You're trying to find where it's concave up and concave down. I pick any number between. I will pick 1/2 and I will pick 2. Now, it doesn't matter as long as you pick any number between 0 and 1. Why? Because between 0 and 1, the second derivative is either always positive or always negative. It can only change signs at 1 because that's the only point where the second derivative is 0 or undefined. So I could put a 1/2, a 1/3, a 0.9. It doesn't matter because the second derivative will be the same between 0 and 1 wherever you pick. And similarly, between 1 and infinity, you could pick any number because the second derivative will always be either positive or negative in that whole region. So you can pick 2, 20, 2,000, 2 million. It does not matter. Okay? Now, I want to know the second derivative at this point here. So what is the second derivative at 1/2? That's ln of 1/2 over 4 times 1/2 to the 3/2. Is that positive or negative? Okay, ln of 1/2. You should all know if that's positive or negative. Right now you're like, I'm not sure, but you know the graph. Here's the graph of ln. That's 1, 0. At 1/2, it's negative between 0 and 1. You should know ln is negative between 0 and 1. So this will be negative on top. The bottom's positive. A negative divided by a positive is negative. So you know now between 0 and 1, The second derivative is always negative. Plug in 2. We're going to do 2 now. So replace all these with 2. Well, that's always positive, clearly, right? How about ln of 2? You should know ln of 2 is positive. Why? For the same reason. It goes through 1, 0. Anything to the right of 1, ln is positive. So we know it's positive, and that's positive. A positive divided by positive is positive. So now we have done our analysis. Now we're ready to come to our conclusions. Let's do this. We know if the second derivative is negative, f is concave down, the function. So we will say f is concave down on the interval from 0 to 1. Why? I'll write out the word. Because f double prime is negative, on interval from 0 to 1. That's one way to write that. There's another way. I'm going to be a little more shorthand on this. So it's positive from 1 to infinity. So we know f double prime is positive, is concave up. I'll say this. F is concave up on what interval? On the interval from 1 to infinity. Now, you can do BC for because, shorthand. And I'm going to say f double prime is positive. Instead of saying is positive, I'm going to say it's greater than 0. I'm just showing you there's different ways you can answer this on a test. F double prime is positive on the interval from 1 to infinity. So there is your other answer for concave up, concave down. That's the manner in which you should write it, one of those two, or a mixture of those two. The last question, they're asking for inflection points. Inflection points occur, the justification is when the second derivative changes signs. Does the second derivative change signs anywhere on this interval? Yeah, at 1. It went from negative to positive. So the last thing you would say, f has an inflection point. At x equal 1, your justification, because the second derivative does what? It changes signs at x equal 1. Bam. You have done the concave up, the concave down, and the inflection point.